Hi all, in today's Proof Without Words series, we are going to look at 5 different visual proofs of the Pythagoras theorem. In the first proof, we are given 2 squares, each of which are subdivided in a different manner. We can see that the first square is subdivided into 2 smaller squares and 4 right angle triangles. We can label the sides of the 4 right angle triangles as A, B, and C, with C as a hypotenuse. The area of the first big square is then equal a square plus b square plus 2ab, which we get by summing up the areas of the components. Now, let's divide up the big square in a different way, with the 4 right angle triangles from earlier lining up the sides of the square. Now we see that there's a big square in the middle of area c square, as well as the 4 right angle triangles, each of area half ab. So the total area is then 2ab plus c square. Since the two diagrams side by side have equal area, we can equate the expressions for area and see that a square plus b square equals c square, which is the Pythagoras theorem. We can now move on to the second proof. Again, we are given 2 diagrams side by side. In the first diagram, we have 4 equal right angle triangles with side lengths a, b, and c, where c is a hypotenuse. The square has an area of c square, since the hypotenuses of the 4 right angle triangles form its side lengths. We can further see that the 4 triangles enclose a square with side length a minus b in the middle of the diagram. Now let's take all these pieces apart as if they are pieces of jigsaw puzzle and reassemble them to get the second diagram. We can sum up the areas in a different manner. First, by noting that we can carve out a square of side length a, so with area a square on the right side of the diagram. Furthermore, there's a second square of side length b, giving an area of b square on the left side of the diagram. By equating the area of the 2 diagrams, we get a square plus b square equals c square as desired. The third proof is quite fun. We are given 5 diagrams in total. The way to understand this is that the shaded area in the initial diagram, which are squares of area a square and b square, are transformed in a series of area preserving operations to finally get the bottom square of area c square, hence establishing the required result. In the first step, the 2 right angle triangles, colored red and blue, are shifted up from their initial base. You can imagine this step to be similar to cutting off a right angle triangle off the bottom of each square and pasting the triangles you have just cut out on top of the squares. Now we can view the new shape we have got as 2 parallelograms. To go from the second diagram to the third diagram, we perform shearing, which is an area preserving operation. Simply put, the bottom base of the parallelograms stay put, while the top bases get shifted in a single direction towards the middle. This is an area preserving operation, just like how the area of a rectangle remains unchanged when we shear it under this similar operation to get a parallelogram. To get the third diagram to the fourth one, we just have to shift the whole thing down. And finally, to go from the fourth diagram to the fifth, the red triangle is cut and pasted onto the piece which is initially missing in the square. This series of transformations shows that the sum of the areas of the 2 squares, a square and b square, is equal to the area of the bottom square, which is c square. And we have again proven the Pythagoras theorem. The fourth proof is perhaps the simplest, but also the most mystifying. Again, we are given the diagram with 3 squares enclosing a right angle triangle in the middle, a setup which is now familiar to all of us. We can divide up the pieces and label them as capital A, B, C, D, and E, before reassembling these jigsaw pieces directly in the bottom square, allowing us to prove directly that the sum of the areas of the 2 squares above equal the area of the bottom square. Finally, we are at the 5th and final proof. We have a circle with radius c, and a right angle triangle with sides a, b, and c for the hypotenuse. Any triangle subtended by the semicircle would be a right angle triangle, and this allows us to deduce, through angle chasing, that the green and blue right angle triangles in the diagram are similar triangles. We can then use the proportionality of lengths of similar triangles to deduce the relationship a square plus b square equals c square, which is what we wanted. That's all for the visual proof. Do know that we haven't gone through each of these proofs in detail, as I prefer leaving out the nitty-gritty and introduce as many proofs as possible. For example, in the fourth proof, I didn't really tell you what is the intuition behind picking the jigsaw pieces and why this method works analytically. I'll leave it to you to fill in the blanks, and please leave a comment if you have any questions or insights to offer, so the others can learn from it as well. I will see you in the next video, and until then, bye.